I'm just going to start recording, and if you have a question, please raise your hand or turn your video on and actually put your hand up in front of the video camera so I see it. That's probably more visible than that tiny little like hand raise icon. I don't even see the hand raise icon right now, but just so y'all know, we are recording. And I should be sharing the screen right now with you that says basic probability. We have 2 chapters, and I think they're pretty straight and relatively straightforward. There's a few confusing things about them, but I think a lot of people have dealt with probability either through sports or gambling or examples in high school. But I think it's more familiar to a lot of people. So I want to get into it. We'll keep an eye on the time as we progress, but just for the people who came in a little bit late, I am recording this session as I normally do, and I'll be uploading that file. And my goal was to be able to have people just sort of chime in, ask questions, make it a little more of a live experience. I wanted to have my face in here for people who weren't actively listening in, because then there's more going on when I'm down in the corner looking at the camera. I don't know if it's more good going on, but it's more going on. So we'll get started, and I have to talk about the basic probability chapter. And I have to be careful because I'll jinx myself. Every time I think it's going to be fast, it ends up taking way longer. But my goal to get through this chapter is like 20, 25 minutes, and we'll just see where we get to. If it's
I was going to mention.
Yeah, go ahead.
I can't stay for the whole session, but I'll be here for a few minutes, and I should be able to make it for through the first chapter at least.
Okay, awesome. Depending on how long I take, of course. But no, we'll make it my goal to get through it relatively quickly, because I know that dragging on longer makes it harder to learn some of these things too. The first, the way that Wheelan introduces this chapter I thought was really useful, which was the SCHLITZ beer example. Does anybody want to chime in with if they've read the chapter and remember this part of it? With the cleverness that SCHLITZ beer did. This is at a halftime Super Bowl kind of. I think it was Super Bowl, but it was a halftime of football game event, nationally televised, and they used the law of large numbers combined with some clever thinking on the back end to make SCHLITZ beer seem really successful. Does anyone remember what it was? All right, I will summarize, and I'm going to go back to my handy little drawing board really quick here. What they did was they asked for, is this not? Huh? Oh, now it's working. Okay. Boy, there was a lag there. I think the computer had to recognize that this thing was turned on. What SCHLITZ beer did was they waited until halftime, and so this is the marketing part of this was. Halftime me. Okay, we're doing multiple things here with my computer, and so there's a little bit more lag than I'm used to working with. It'll be okay. I just want to point this out, not from a laws of probability standpoint, but from a clever marketing perspective. If any of you are going into business, some of you have said you're going to already. If you're going to try and find people who like cheap light beer, wait until they're drunk, and you'll have more success because your taste goes down. And so as people who can tell you who don't like a beer on their first sip and like it more on their fifth sip, and they like it even more by the time they're in their second beer. So they waited till halftime, and they asked for a voluntary sample of 100. Oops. Ugh. The lag is killing me. Let's see if I can get it out of here. You know what? Actually, I can just I don't know if the tablet's going to work in this setup because there's so much lag that my usual barely getting it out there is really bad. So what we'll do is we'll just start up a new Google Documents. No, I said wow, there was a lot of, I helped somebody upload their testing files for a Canvas class. That was what all that hot mess was. All right, so Schlitz's cleverness, and I will make this bigger and some bulleted points. They waited till halftime. That's just an ancillary point. That doesn't have anything to do with the probability, but it's cleverness because, as I said, people who've had a couple beers are going to be a little bit more, a little less good of a taster. It's why people, when they're tasting wine, spit their wine out partway through, right? And they asked 100 non-Schlitz drinkers to volunteer. I'm going to make this even a little bit bigger because we don't have that much to do here. That part is important for this this to be successful. If they asked people who already drank Schlitz to engage in a blind taste test of Schlitz versus some other beer, then they'd have a very real risk of having people choose away from Schlitz, which would look terrible. But by having 100 non-Schlitz beer drinkers come up and try Schlitz randomly, they're only going to find people who said they didn't like Schlitz and will say they do like Schlitz. Even if 20 out of 100 said, oh, I do like this Schlitz, because they couldn't taste anything because they'd already had 2 beers. Even if it was a relatively small number of that 100 that said Schlitz, they're still winning because they could always say, look, people change their mind from their favorite beer to Schlitz. And their whole goal is just to get people to try Schlitz, right? They want people to go out and buy it and try it and think that it's okay because it's a cheap mass market beer. And then they did a taste test. A leading brand, and who knows what that leading brand was? I don't remember if Whelan actually named it or not, but a leading brand and Schlitz. Marketers are careful about this sometimes when they don't want to have other companies be too mad at them and maybe threaten suit if they're trying to make unfair comparisons. But a leading brand is Schlitz. And the cleverness here that goes into this with probability is Whelan points out that if they'd done it with 10 people and they thought that the likelihood of people saying they preferred Schlitz in a blind taste test was about 50%, with 10 people they could have had as few as 2 or 3 people still say they like Schlitz, whereas with 100 people they knew they were going to get somewhere around 50 people saying they like Schlitz more than the other beer. So the point Whelan is making here is that by choosing a larger sample, a larger number of people, they were going to approach the actual probability of people turning from Schlitz to another beer. Now, here's the other cleverness. Let's suppose that there's no difference between, let's say, I don't like leading brand, I'm just going to say PBR. That's my favorite cheap beer, but you all don't need to know that. And if there's no difference in taste between PBR and Schlitz, and don't anybody be mad at me if one of these is your favorite beers and you think the other one tastes badly, tastes terrible. Let's suppose, just hypothetically, that there's no difference between PBR and Schlitz in terms of a blind taste test. In other words, people can't really tell the difference. If that's the hypothesis, then what would we expect to have be the choice of 100 people if they're given an unmarked cup of Schlitz and an unmarked cup of PBR, and there really is no difference between the two? How many people will say they like the Schlitz and how many people will say they like the PBR on average? Someone want to go for it?
It would be an even split, like half and half, 50-50?
Excellent. it's an even odds thing, right? If there's really no difference, if you can't tell the difference between the two beers, then you're going to choose one of the beers half the time and the other beer half the time. So Schlitz really was banking on the fact that all cheap beer tastes like cheap beer. And so by doing this taste test, they got 100 people who all said, no, I love PBR, or no, I love Milwaukee's Best, or no, I love whatever other brand, right? And then they came up and they took a blind test, maybe a little buzzed, between Schlitz and some other beer, and half of the people, just through dumb luck, through random chance, would have selected Schlitz beer. Everyone follow what I'm suggesting here?
Wouldn't it be likely, though, that at that point in time they would have already been pretty buzzed on drinking whatever their normal beer of choice was, considering it's halftime at Super Bowl?
Yes, which was the first point, which is at halftime of Super Bowl, your taste buds are going to be dead enough that you're already talking about not being able to differentiate very well between two different beers.
So they're basically stacking the deck to get people to create. They're basically creating or manipulating a probability to make a good marketing ad.
That's right. So in other words, I mean, if you're going to spend a lot of money to do this kind of thing on national TV, you don't want to have it go wrong, right? And so that's exactly right. And so the cleverness that Wieland's alluding to here is that it wasn't just that they had an underlying idea about the probability distribution. It's also they knew that they couldn't really go wrong. And let's say that and part of it was 100 people. If they had 10 people, now if I toss a coin 10 times, is it going to come up 5 heads and 5 tails every time?
No.
No, it might come up 6 and 4 or 4 and 6, right? If I toss a coin one time, it's going to come up heads or tails. It won't come up half and half. So by getting 100 beer drinkers out there, they're making it more likely they're going to get somewhere closer to 50-50, even if there's no difference between the beers. And that was part of their cleverness, was getting enough people out there. And it looked impressive because the message it sent was that, hey, if you're drinking another beer and you think it's your favorite beer, look at all these people who changed their mind in a blind taste test, right? The message wasn't, look at who can't tell the difference between Schlitz and some other cheap beer. So it's pretty clever. All right, moving on. And I just bring this up in passing. I'm not going to spend too much time on this because I want you, if you're curious about this, to think about it. But we see this kind of statistical claim a lot. We're going to get back to this idea in Problems with Probability. Wieland brings it up in his chapter 6 as well. But the FBI has this claim that the chances of a 9 loci, I don't know if it's loci or loci. I think it's loci. Hard C or soft C? I don't know. Match between 2 unrelated persons are 1 in 113 billion. In other words, if you have a 9 loci match, then it's, there's only 7 billion people on the planet, and maybe they're relatives, but that's pretty low odds. The problem with this, though, is that if we search DNA databases, we find 1,000 pairs of those matches. Wieland leaves it at that, which is a little disingenuous, but he just sort of like ripples the water a little and says, well, there's some things going on here. At the very least, the implication is that, maybe there's a lot of relatives all in DNA databases. That's possible, right? People from the same family might be more or less predisposed to criminal activity and therefore having their DNA entered into databases. But the implication as well is that the FBI was overstating that likelihood. For those of you who are curious about this, and by the way, I've acknowledged already that everyone brings bias into the classroom. I want to make sure that I don't sound overly biased about a lot of stuff. One of the things that people get out of this little lesson from Wieland is, the FBI is not good about using DNA evidence the right way, and so that's bad for the FBI and good for criminals if you like law enforcement, or it's bad for the FBI, or it means the FBI is not doing the right job if you don't like law enforcement. Let me unpack that a little bit further here, which is under this optional material. If you're curious about this sort of thing, and like I said, Wieland doesn't really get into it in detail, but this is an optional reading, so it's not assigned. But for those of you who want to look into this, one of the things that we assume about DNA testing and reinforced by all the crime shows in the universe, right? Like CSI, they're like, oh, I found a fragment of DNA, and now I know it is, the prime minister of Kyrgyzstan, whatever. There's these crazy plots that revolve around finding little traces of DNA, and that's all you need. There are big problems with DNA testing today, and it cuts both ways, whether you're sort of a pro law enforcement or anti law enforcement. There's challenges to this both ways. The reason I bring that up is because DNA testing today is really important for the exoneration of wrongfully convicted individuals. So DNA evidence can be misused to secure a conviction that shouldn't be done, but it can also be used to free people who have been wrongly convicted. So we want to make sure we have good DNA evidence is the message I have. It's not about being pro or anti law enforcement or pro or anti individual rights in that regard. But I'm going to leave it at that because I don't want to draw too much extra material into this class. But Whelan brings this example up, and I wanted to move on past it with that further reading if you're curious about reading about it. The short story, for those of you who want the Cliff Notes version, is that one of the big problems we see at DNA sampling is problems with contamination of samples, problems with the custody of samples, and problems with their use in the lab. So there's a whole lot of things that happen between all the way from the collection of DNA at the crime scene or from an individual all the way through to sequencing it, right? So it's not just like it gets scanned and entered into the database all in one step. And that's the short story about that article. Anyway, let's move on to probability. The way we denote probability in short is P and then a something inside of it. And so I'm going to go back to sketching here and see how it works, give it another shot. But I'm going to try and use this. I'll just write slowly. Oh, wait, what? No. I tried to erase. I swear I did. Okay. Now it's erasing. No, now it's drawing. So the pen has an eraser on it, just so you know what's going on here. And I'm using the eraser, and it's mostly working, but every once in a while it decides that I'm not trying to erase, I'm trying to write, which was leading to all that squiggling. Like that, too. No! Stop, pen! All right, that's close enough. We're going to go down here. So the way we denote a probability of something is we might write something like the probability of a coin toss coming up heads. Oh, I don't think the pen's going to work. That was my honest try. We'll just go back to the Google Doc. Google Doc's working better. Wait, what? There we go. All right. So the way we denote this actually works fine. You're going to hear my clacking on the click keys, but the probability of a coin toss coming up heads is, as we already, and I'm going to write this on the top just to be super clear. And we're assuming the coin is fair. We're assuming that there's nothing trick about it, right? And the way we denote a probability is as a ratio. We can put it as a 0.5. And we can also say the probability of tails equals 0.5. And we can say the probability of heads. And in statistical notation for probability, you do this. It looks like a slash because it is a slash. It's just a vertical slash. The probability of a coin toss coming up heads or tails, is it ever going to fall on its side and land on its side, everybody? In real life? Anyone?
No.
I mean, if you're lucky, you might get a roller.
You might get a roller. Fair enough.
16 probably.
but then it's eventually going to fall on
one side.
one or the other, right?
Right.
And so what we see is the probability of heads or tails is 1.0, which is the same as the probability of heads. Now, by the way, if you're math phobic and this is triggering all that anxiety from years of math classes where someone would write a formula on your on your board, don't worry, we'll convert this to English in a minute. I just want to get it out there so when you see it, this is the same thing. So the probability of heads plus the probability of tails is the probability of heads or tails is 1, right? Because the probability of heads is 50% and probability of tails is 50%. So here's the way we'd write that in English.
Professor, I don't mean to
Yes.
interrupt.
No, that's okay.
Were you planning on recording this?
It is being recorded.
I don't think it's being recorded on Zoom.
It's not being recorded on Zoom. And we had
Oh.
that suggestion already, but I'm recording it using my little face in the corner software.
Perfect. Okay, I
And
just
so,
want to double check.
and I don't know if that's a good solution or not, but I'm trying to figure out how to use Zoom still too all the way. And for whatever reason, I couldn't get the chat window to come up on this session, and I wasn't going to try and shut down and restart the session. And I just said, it's good enough. It's going to be, it's gonna be what it is. So
Okay.
that's why those of you who are live in the session can't see my face, but those of you who are watching it recorded have my face down in the corner. There's lots going on.
I see.
But yeah.
Gotcha.
Yeah, thanks for bringing it to just checking. Thanks.
Yep, no worries.
Yeah. Okay. So the first thing we just said is there's a 50% chance the coin will toss will be heads and a 50% chance will be tails. We've just made that in this P notation here, right? And then the last thing I said, there is a 100% chance So this might seem really elementary, but I just want to make sure we sort of get that out there while we're talking about what the P's mean, because I think people get confused by it sometimes. This is the wrong slide deck. There we go. The probability of event A happening and event B happening is the probability of each of those events times each other. And then the probability of A or B happening is those probabilities plus each other. And let's go back to my little example here. I just said that, right? Which is the probability of A happening or B happening is, I can emphasize the or here, is A plus probability of B. Okay. Let's take this example though and say, what's the probability of first landing a heads, then tails, if we want to calculate the probability of a heads and then a tails, let me change my view here so it's a little bit less. There we go. And I'll zoom in on that a little bit. If we want to calculate the probability of heads then tails in two tosses, we need to figure out the probability of heads. Everybody, what do I do? Anybody, what do I do? Uh-oh, filter keys. It's times the probability of tails. Equals 0.5 times 0.5 equals 0.25. Now, 0.25 is a quarter. This might not seem intuitive, but it's based on the way I asked the question. I said the probability of heads then tails in two tosses. I didn't say what's the probability we'll have one heads and one tail. I said heads then tails, so the order was important. So if we think about it, if I toss a coin and then I toss it again, in 2 tosses like that, then I could have heads and heads. I could have heads then tails, which is what we were looking for. But I could have tails then heads, and I could have tails then tails. Is this making sense to everybody? Okay, I see some heads nodding. So does everyone see how the specific probability of heads and tails is 1/4 of all possible combinations? So we could toss it twice and get heads heads. We could toss it twice and get tails heads, and we could toss it twice and get tails tails. But 1/4 of the time, we'd expect to get heads tails. Now, we won't get it every single time, and we won't get it exactly 1/4 of the time, but on average, that's what we're expecting. So this is that. Make sure I get back to the right one. Here we go. The probability of A and B, with event A being specified as heads and B being specified as tails. All right. Now, we assume independence, meaning that the outcome of the, independence means that the outcome of the first event, the outcome of the second event isn't influenced by the outcome of the first event. So the probability of being, let me give you an example of not independent events. The probability of being bitten by a shark is highly dependent on going swimming in shark-infested waters. And if you have a really low probability of going swimming in shark-infested waters, then your probability of being bitten by a shark is extremely low. If you love going swimming in shark-infested waters, then your probability of being bitten by a shark is much higher. Does everyone see how these 2 events are not independent?
I saw a really funny statistic that in relation to the planets in the solar system, you have a 0% chance of shark attack in Mars, but a 100% chance of shark attack on Earth.
That's right. That's right. There was an early data meme where it was.
That's a good one.
It showed a list of all of the planets, and I think they even had 9 planets because Pluto was included. But the list had each planet, and then it was a table, but each planet had a little picture, and then it was like number of deaths, and there were no deaths with any planet except for Earth, which had like 80 billion or something since the beginning of time. It was like 100% correlation between dying and being on Earth. Yeah, that's a great example. Thanks. All right. So independence means that the first event isn't, the second event isn't contingent on the first event in any way, right? Now, when we get into the probability of A or B, we have to assume mutually exclusive outcomes, and Venn diagrams come in handy here too. And I'm a little bit limited with my illustration capabilities right now, but let me see if I can just can I insert a drawing, table, chart? If it was Microsoft Word, you know what? There's no reason I can't put Word on here for you. Oh, yes, I can't because it's sharing on Zoom. Ugh. And it's hard to share the same. Here, I'll do it like this. I don't always feel clever when I'm trying to figure out how best to illustrate something, but I'm going to take my chances and try and go back here to this diagram, and I'm going to actually see if I can do it freehand with the mouse, because that might be better than trying to use a tablet. Ooh, it is better. All right. The example that Whelan gives is a really good one if you've ever played card games. If you've never played card games, it might be a little bit more abstract. But there are 52 cards in a deck. There are 13 of each suit: clubs, hearts, spades, and diamonds. So 4 suits of 13 cards each, and then the cards have a 1 through 10 on the face, an ace through 10 on the face, and then the jack, king, and queen. So if I said, what's the probability of drawing a, my cursor just disappeared. There it is. Okay. What's the probability of drawing a 5? Somebody quick, how many 5s are there in a deck of cards?
4.
Okay. And so my probability is 1 out of, that's right, it's 4. So how many suits are there? How many different 5s are there? 4 different 5s. Here, let me switch it up like this. Probability of drawing 4 out of how many cards in the deck?
52.
Good. And what's 4 out of 52 reduced to, fraction-wise?
One eight.
Is it 1 out of 12.5?
13.
13. There we go. Yeah.
Yeah, there we go. Good. And then the probability of drawing a heart, any heart card.
1 out of 4.
That'd be 1 out of
13
13.
out of 52, yes, equals 1 out of 4. Everyone with me?
Mm-hmm.
Ish? Okay. So now, if we naively, quickly, somebody says, quick, answer this question. Sorry. Now, I said a 5 card or a heart, right? So when we look at the or, we want to add the probabilities. And so what we intuitively want to do is add 13 plus 4 and have 17 50 seconds, right? We add the probability of a 5 or the probability of drawing a heart. Except for...
Oh, one of the cards is both.
One of the cards is both. Excellent. That was perfect. One of the cards is both. And so you need to think about the cases in which there is a 5 of hearts, and you can't draw the 5 of hearts twice. It doesn't exist twice in the deck. It exists once as a 5 in the deck, and at the same time, it's once in the deck as a heart. So that's where our Venn diagram comes in here, which is there's 3 cards that are 5s that aren't hearts. This is sloppy, but that's okay. There's 1 card that's a 5 that is a heart, and there's 12 cards that are hearts that aren't 5s. So this circle is all the 5s. 3 not hearts, 1 heart. This circle is all the hearts. 1 5, 12 not 5s. Everyone smell what I'm cooking? So when we think about the odds of getting these cards, we need to take this 12 plus the 4, or this 3 plus the 13. We don't count the 5 twice. So 12 plus 4 is 16, or 3 plus 13 is 16. And our answer then is 16 50 seconds, which my math brain works really slow when I'm in front of a group. So so that's 8/26 or 4/13, right? Is that right? Yes, because I divide both by 4. Okay. And if we wanted to express that as a fraction, we could go to a calculator and say, Google just does it for us. If we put it, nope, I get Bible verses.
It's right around 0.32. It's just a little less than 0.33.
Right, that makes sense. I'm going to do it just for good measure. 0.307. Yeah, so about 1/3 of are your odds of drawing that. All right. Any questions, or are we ready to move on?
I was just gonna say I've got to run, but
Okay.
it was my pleasure. Thank you guys, and I'll be sure to watch the rest of the lecture when it's posted.
Awesome. Yeah. So I was confident about being done quickly, and then this is exactly what I was worried was going to happen, but it's okay. We're going to move through it.
Absolutely.
Let's
I'm figuring it out. Y'all take care.
Yeah. Thanks,
Yeah,
Chris.
you too, Chris.
Yeah.
Thank you.
There's a little button you can say go faster if you want, by the way, everybody. Just saying. All right. Expected value gets into this idea about adding probabilities. So we just talked about how we come up with joint probabilities for independent events or mutually exclusive outcomes. And the example that Whelan next works is this idea about how to calculate the expected value of one transaction, for example, buying a lottery ticket. Now, this can be really complicated if we don't know some things about the lottery, like whether sometimes you buy a lottery ticket and there's no winner, right? And then the pot increases. But some really basic lotteries have known odds of winning because they just print the tickets that are winners. They don't do a random draw for them. In those cases, the calculated value of a ticket is fairly easy to figure out. What we've done here is we've figured out the odds of winning each prize and multiplied the prize amount by its odds of winning. So we multiply, you have a 1 in 15 chance of winning two. So you imagine this ticket you've bought, you haven't scratched the ticket yet off, right? Or you haven't pulled the tab if it's a pull tab. And it's just unknown. You don't know what's behind that little silver sheen of the foil on the ticket. So there's you're imagining it could be the $1,000 prize, but it could also be a $2 prize, or it could also be nothing. So knowing what we know about the odds, we know there's 1 in 15 of these cards are a $2 prize, and so we assume that it could be a $2 prize, but it's only going to be a $2 prize 1/15 of the time. But it's also a $4 prize 1 out of 42.86 times, and I'm not sure where that came from exactly, but that's the odds. And then there's a $5 prize 1 out of 75 times, and a $10 prize 1 out of 200 times. So the idea here is, let's suppose, back to this example of earlier, let's suppose that you go back to here. Let's suppose that your probability of winning one out of 15. If I buy 15 tickets, how much will I win? On average. Anybody? I'll win $2, right? But the other way to say the expected value of each ticket is $2 divided by 15. So each ticket's worth 13 cents and change, which is what we're saying here. If I spend $15 on tickets and I win $2, then the actual value of each ticket was worth 13 cents, right? The one ticket's worth $2, but 14 tickets are worth nothing. Now, of course, we can have different values behind each ticket, but the odds get worse with higher prize values. I don't know if I made a mistake here. I've made a mistake once before in this class. This might be the second time I made a mistake, but the point of this is that because you'd expect the odds of winning the higher prize to be higher than the odds of winning the lower prize. So I don't know if I just copied down the results wrong or what I did wrong there, if anything. But I'm looking at this again and being like, did I write that down right? But what we do is we look at the odds of winning each prize times that prize value. And $1,000 is a lot of money, but you're not really likely to get it. And so it's not a lot of money in terms of expected value. The calculation that Whelan makes here is that it's approximately equal to 56 cents. And he has some caveats about why it's not exactly 56 cents, having to do with the fact that you could win another ticket, and winning another ticket then gives you another chance to win. But the point being is that if you buy a bunch of tickets for $1, and expect to make money on just buying millions and millions of tickets, you're going to go broke, and you're going to lose on average 44% of your money, because the ticket's expected value is less than the dollar you're spending on it, which is why lotteries exist, right? Lotteries exist because the people selling the tickets make money, and the people buying the tickets on average lose money. People just win money once in a while. This brings up the idea of the law of large numbers, which is that the lottery commission would never let you play a lottery where they sold only one ticket, because they wouldn't want to lose all the money. They want to be able to sell enough tickets that they're making a lot of money despite paying out some of the bits. We've already talked about this with respect to the SCHLITZ beer example, which is that if we only have 10 tasters, their most likely outcome is 50-50. But we also have a fairly likely outcome of 40-60 and a fairly likely outcome of 60-40, and a not unexpected, like 10% outcome, 10% likelihood that we'll have only 3 out of 10 people tasting Schlitz. The law of large numbers states that the more often we repeat a random process, the more the average converges on the expected value. That's true about the Schlitz beer case. It's true about lotteries. So here we see 100 trials, and the underlying expected value is 50-50. Schlitz knew that it was very unlikely they'd have fewer than, say, 40 people choosing Schlitz, and they might have up towards 60, but it was most likely around 60. If we saw it doing for 1,000 people, it would have been almost on 500. By the way, there's a quick thing here for those of you who are like visualizations in particular. There is this link here, the last link under the optional bonus material. And so this is optional bonus just if you want to learn about stuff in a different way. But we have expected values, and there's a good example of the law of large numbers here in terms of chance events. We flip the coin and we get heads, and the expected outcome is 50-50, and it's 100% heads. And what are you talking about? But I can flip the coin 100 times, and what I see is it comes out 54 heads and 46 tails. And I can flip it 100 more times, and now we've got it 53% heads and 47% tail. And I can do it 1,000 times.
Hey, Professor, I had a question about that lottery example.
Yeah.
A lot of lotteries, I don't know about other people, but I always kind of got the sense that the lottery amount increases based on how many people buy tickets, and the cost basically goes into that lottery. But so there's no guarantee that the actual amount being awarded is the same as the value of the tickets being bought. So isn't it also possible that like maybe $2 billion worth of tickets are bought, but it's only like maybe $200 million in prizes being offered? So no matter what, they're making a massive profit, even if they do like have to pay out a big winner.
Yes, that's very much the case, and that's especially true with these lotteries that. So I brought that up at the very start of the discussion about this, which is that some lotteries don't guarantee winners. Mm-hmm. In other words, if it's a lottery where you choose the numbers and then they choose the winners by drawing numbers randomly, which is like Powerball kind of lotteries. I'm not a huge lotto fan, but I'm familiar with the practice, right? But that's the kind of thing you're talking about, right? Like these, like the Mega Millions.
It's not like a raffle where everybody gets the total, or like one person gets the total amount. Like they get the amount that the lottery people decide is the grand prize.
That's right. Yeah. Even so the thing you're talking about specifically is that the more people that play some of these lottos affects the odds of winning the lottery, because more random numbers means a larger odds that there will be a winner. So the more tickets they sell, the more people will play all kinds of random numbers. But also, there's no guarantee that they'll pay out the winnings. And they do increase the prize, but they don't tell you by how much they're increasing the prize. And so in that case, we don't know. You're exactly right. We don't know what the actual odds of winning are, because it depends on how many people bought the tickets, and I mean, you can tell the odds of a certain number coming up, right? But you can't give an expected value for a given prize based on that.
Well, and the increase of odds is not necessarily matched by the increase in prize amount either.
That's right. Well, if somebody chooses the same number as you, you split the value, right? Yeah. That's right. So that's complicated. You're exactly right. This example that Whelan chose is one that has a fixed prize ratio, and so the tickets are printed and the prize is either under the scratch off or it's not. Mm-hmm. So when you buy the ticket, the odds of picking a winning ticket aren't affected by a chance event off the ticket. Does that make sense?
Yeah.
Yeah. So this example is a good one for us understanding the expected value of something that has what we call in mathematics a finite choice set, right? That's really fancy terminology for it, but we know the rules of the game aren't in flux based on some random chance, and the random drawing of balls from the hopper is a great example of a chance event that we're trying to guess at, but the odds of a match. Now, so interestingly, the odds of a match don't change with the prize amount, but the expected value of the payout would change, right?
Mm-hmm.
So you could calculate the odds of winning any given, ball drawing lottery based on the number of balls, and it's like astronomically hard, right? Because it's not just like to win I think most of these, somebody correct me if I'm wrong because I'm not that familiar with these lottos, but don't you have to match the numbers in the same order, or is it just matching the numbers? Does anyone know?
I don't, but I think I'm not for sure, but I do believe it's the same order.
If it's the same order, it's the same problem we had with the heads or tails, right? It's not tails or heads. In which case, it's like, yeah, man, good luck getting all that matched up, which is why these things go on for a long time sometimes. But yeah, really good point. Thanks for bringing that up. Which is that this case is one where we know the expected values relatively easily because the prizes are set and the answer is waiting for us behind that little scratch off. It's not sort of out to the winds of chance in terms of where the ball goes, right? All right. Decision trees. Whelan gets into decision trees a little bit. Decision trees, I like to take a minute to explain, not because I want people to feel confused about them, but because we do have a lot of students interested in business-related stuff, policy-related stuff, and there's a lot of places to go with decision trees. So I think without tapping on this point and saying, hey, this is really useful, I think a lot of people say, that's confusing, I didn't get it the first time, and then they sort of give up. But I put this example here of a couple different project options where you're a firm and you're deciding whether you're going to invest in or propose a project and then get a contract to produce some kind of an invention. And I just got this off the internet. I don't remember what it was proposed, but it's an example. But if we look here at the start, let's say you have $20,000 to spend, and you can either spend the money preparing a proposal to try and get a contract, or you can, stop that, Google, stop that. There we go. Or you can take the fixed fee project, in which case it costs less money to do the fixed fee project, and your outlay isn't as expensive. But let's suppose that you prepare the proposal and you don't award the contract. You've lost some foregone income. If you're awarded the contract, you get money, but then you have to decide how you're going to invest it. And you can sort of make these projections. Now, all these projections have probabilities associated with whether they're going to be successful or not. This is entirely up to your own modeling, and sometimes this can be really uncertain. But the whole point of the decision tree is to think about the steps along the way about how you're going to spend your money or invest your money or save your money. And then the expected value of all your decisions is the sum of each outcome times its each respective likelihood of happening. In other words, if you have a 50% chance of being awarded the contract and earning $90,000, but a 50% chance of being not awarded the contract and being awarded, costing you $50,000 total to not get the contract, then your expected value is 50% times 90,000 plus 50% times negative 25,000. So you would go for this if you were confident about these odds, because more often, if you are more often than not rewarded with contracts that are worth more than the cost of being not awarded those contracts, then you're going to come out ahead. Whelan puts this in, this is another example of that, just showing the math. And so I'm actually going to fast forward through this because I don't want to kill everybody here with boredom. But Whelan gives us this example of a decision tree in terms of testing. And he says, well, let's suppose that we are looking for HIV/AIDS in the adult population of the U.S. We want to screen all adult Americans for the presence of this virus with the idea of really worrying about testing and tracing it. By the way people are talking about doing with COVID-19, but in a different context, obviously. But let's suppose that 1 out of, let's do my math, 10, 100,000, 10,000, 1 out of 100,000 people have HIV, they're HIV positive. So therefore, everybody else doesn't have the disease, right? And then let's suppose that the people who are positive, now every test has a different measurement sensitivity and specificity. I don't want to get into the details on that, but basically some tests are more accurate at detecting the thing they're meant to test, and other tests are not as accurate. The test that we have for HIV is really good at giving positive results for people who are actually positive. So everybody, 100% of people who test positive that have the disease test positive. So that's really good because we want to make sure that we correctly identify people with the disease. So nobody tests negative. So nobody's in the group of having the disease and testing negative. However, the problem with the HIV test that we have, as well as a bunch of other tests, is that there is a fairly small, but still it exists, even though it's small, what we call a false positive rate, which is that of the people who don't have the disease, a fraction of them still test positive. So the outcome of testing all 175 million adult Americans with the HIV test that we have right now is that we would have 17,500 false positives. So we'd have people come back with a positive test that didn't have the disease, right? And we would be generating that many false positives to discover 1,750 people who did have the disease that tested positive, right? So the implication here that Whelan brings to us is that testing everybody in America might seem, it's been proposed, let's put it that way. I don't want to say it's a good idea to anybody, but it's something that people have put out there at some point or another. But we're going to end up, if we do that, with 17,000 people we have to call and say, hey, we have the results of your test. Can you come back in? Right? And that comes at a great social cost. And in order to find these 1,750 people who are in need of care. So medical professionals deal with this sort of math a lot, where they say, what's the cost to society and the cost to medical systems as well of doing extensive testing, right, versus the potential reward. So with HIV/AIDS testing, it's generally speaking not done in a general screening way. It's done for people who identify, self-disclose as having risk factors or being concerned about it, and then you get an HIV/AIDS test, right? It's not an AIDS test, but it's HIV leads to AIDS if it's left untreated. So it's this interface of the really low probability of being falsely identified as a positive test that still prevents the medical system from just sort of giving a blanket HIV test to everybody, because the actual incidence rate of it is low enough that it's not justified in the medical system. I don't know if I explained that as well as I might have. Is it anyone have questions about that? Or all right, we are almost done with this, and it's been man, I'm gonna eat my words. I said like 20 minutes, didn't I? I live and learn, or I live and I don't learn, because I already said that at the beginning. I said I'm gonna knock on wood. I'm gonna hex myself here, but let's get on the last bit here. One of the things that Whelan brings up at the end of this chapter that comes up into full force in the next chapter is the use of statistics in what we call predictive policing or predictive analytics, and we do this already. Corporations in particular do this. Marketing is the sort of the tip of the spear on this. Marketing's been doing this longer than a lot of places, but lots of different firms and governments are getting into big data and using a lot of publicly available data, a lot of marketing-based data that we very often willingly surrender without realizing how much it tells governments and firms about us. And there are huge implications for it with respect to our organization as a society and ethical implications about it as well. I am going to get into this really briefly with us, meaning like 3 minutes-ish here. But I want to pull up these examples just to get it, to illustrate what I'm talking about here. This optional reading here, if you want to read more about it, you can check it out. This is a 2012, so 8-year-old article that talks about, like I said, the tip of the spear on this was in marketing, where companies with the reward cards are tracking user data about what people are buying and how their purchases change. And the anecdote that's really powerful in this story by Duhigg is about Target and how a Target customer service manager had an irate man come in and brought in a pamphlet that he'd been given and said, "Listen, I don't know what's going on here, but you sent my teenage daughter a getting ready for baby marketing brochure, and she's 15 or 16. I don't know what the exact case was. You can read the story if you want." And now the anecdote was phrased in a way that made it seem like, haha, what a laugh, right? But the point is that a couple weeks later, the same manager had a visit from the dad, who came around and said, there's been some things going on in my house that I didn't know about, and I apologize. So in other words, Target knew that his daughter was pregnant before he did. And on the one side of things, it's like, oh, that's, interesting, and what a crazy world that is, right? But it's also creepy AF, I hope you agree, that Target's able to tell when a teenage girl is pregnant based on her purchases. That's how they told. That's how they knew. Was that? And I don't think she bought a home pregnancy kit. I think it was from people, pregnant people. Their sense of taste changes. The sense of smell changes. They tend to buy different foods, right? And so her purchase history flagged her as pregnant, even though Target didn't know how old she was. They just said, "Oh, this person's pregnant."
It actually gets nuts in that if you think about it, because a lot of media now and companies are going not just off of purchase history, but just search history.
Yes, absolutely. So big data is this is a 2012 article, and it's based, the story is from longer. If you want to get into this article right here, this Stan, Mickle, and Curran article in the Wall Street Journal is fascinating, and I put it in as a PDF because Wall Street Journal likes to paywall stuff. But they track how much. They just imagine that you order pizza and go over to a friend's house and watch a movie on you pay some service to rent a movie online, and it chronicles how much of your data is tracked, including your location, including the settings on your phone, including other apps that are open in some cases. These are all different, and so by the end of it here, it's like, this is everything that Google tracks about you while you're using their apps, right? So it's just fascinating that the amount of data that we have out there. And the challenge we have here is that we do this in the name of convenience very often, but firms are actually actively interested in risk management on this too. So predicting behavior. Does anybody have a car insurance program that gives them a discount based on their driving behavior?
Yeah, I have that from State Farm. They basically send you a little Bluetooth recording device, which I think is like GPS/G-force, which kind of determines how hard you're driving, like how hard you brake, how quick.
It tracks how hard you accelerate, how rapidly you slam on the brakes, how much you swerve, how fast you drive,
what kind of car you own.
Yeah.
And
right?
And if you get a good rating, which goes on like a bi-weekly basis, some kind of discount, which I don't even know how they determine that.
And it also tracks your total miles driven, right? Because the more miles you drive,
Yeah.
statistically, the more likely you are to be in an accident.
Yeah.
Yeah. And so, so we see this kind of thing happening at this really fine scale level where, like, yeah, we opt into it, right? But pretty soon, if everybody opts in, then the people who opt out are going to be the bad drivers. And so then they'll know about you being a bad driver from you not opting in. It's kind of a catch-22 that way. And so this is a little bit problematic. And sometimes people say, well, that's about the insurance company. And we have all kinds of ways of justifying some of this stuff. But let me give you one more example, and this will hit close to home for some other people. Your biological sex determines how much you pay for car insurance too, and your age determines how much you pay for car insurance. So when I started buying car insurance as like a 17-year-old male, I was outraged, right? Because I wasn't a bad driver. Honestly, I was, but I didn't feel like I was a bad driver, and I didn't deserve to pay a higher premium than a older person or a woman would, right? And so this is the kind of thing where the insurance company or the marketing firm has a probabilistic estimate of how likely someone is to be in a wreck based on some kind of characteristic they have, but it may not be fair to that individual person. So that's the ethical debate around that. All right. That wraps up that chapter. Anyone have any quick questions or comments? I went a little fast through some stuff and a little slow through others, but hey, it took us an hour. On the other hand, in a regular classroom, this would have been the time for a break, so I don't feel too bad about that. Usually I just am a little more directed up about just recording a lecture with no Q&A. All right, I am going to end it there. Thanks for joining me, those of you who could join in, and I will see you all again soon for I'm going to announce I was thinking we might get started on this one today, but I'm going to end it here because I've been talking long enough and people have been listening long enough. I might try and do Thursday at the same time because that's when our class was going to meet, and I just want to get on a schedule where I can not procrastinate anymore by letting the perfect or even the good be the enemy of the okay. So look for an email from me announcing that, but let's tentatively plan on Thursday at 1 as well for that.
Hey, Professor.
Yeah.
For the video quizzes, can we expect them to be done in like the normal Canvas format, or are you going to be doing those embedded quizzes more often?
So since you're here, give me your feedback about, do you like embedded or after? Anyone have an opinion?
I don't mind the embedded ones. I don't.
My only complaint with the quizzes is that sometimes the questions are worded confusingly, so I'm not quite sure what's being asked.
Yeah. Okay.
Particularly like
I'm
when
not doing that on purpose. Honest.
Tim thinks this article has to do with this.
Oh, okay.
Reading the article, I'm like, I'm not quite sure if the article fits either of these options.
Okay, yeah. So I try and use that kind of language because I don't want to put words into the article's mouth, so to speak, into that author's mouth, right? And I might have a take on it that's slightly different than something else, and so I like to ask you about what I just said in the. So I'm not asking you what the article says so much as what I said about the article in the video. Does that make sense?
Yeah.
Yeah. But I'll have to be careful about that. And so you can always just shoot me an email saying, hey, you asked this question, right? And so one of the advantages of having the quiz, so where I'm at with the quiz format, and again, if anybody else has opinions about this, I'm happy to hear them, but embedding the quiz in the video, I wanted people to be able to take it twice or 3 times if they wanted, but then there was a problem with the scores not updating, and it just seemed like it wasn't perfectly integrated.
Scores would update as long as you answered all of the quiz questions, which sometimes when you click on that little arrow up, I mean, I felt like in this too because I was waiting for the grade to update and never did. I found out you have to scroll down to get to all of the quiz questions because they only show like the first 3 questions.
So if you say retake, you have to retake them all.
Yeah, basically.
Okay. Yeah. Okay. Wow, that's rough. So I thought it was a little bit kludgy I like the idea of it just being like a little check right in the middle, like, hey, what did I just say? but I also thought it was, and I got some feedback from students that it was confusing and difficult just because it was in the middle and finding the spot. And using the menu at the bottom was a good shortcut to that, but still the update problem was there as well.
Yeah.
So my idea was to have this where you could have it open, the quiz open, and then also have the video and scan through if you needed to review. Or if you wanted to ask me a question, you could always just like email me about it and say, hey, this question is really confusing. What do you mean? What do you mean?
Yeah, because like the most recent quiz, I think it was for 4.2, I couldn't find the video on Canvas, so I had to go to your YouTube channel to find the video.
Oh, really?
Yeah.
Did it not upload?
Let me double check if it's there. Or yeah, since you're already there.
It's going to be under Panopto. Sorry, I'm looking in the wrong spot.
Is it Panopto?
Yeah, it'll be under Panopto, yeah.
Okay, I've seen that on every Canvas page. I've never used it.
Oh, so there, yeah, this is where all the, so if you want to review any, they're all under here.
Okay.
And there's all the ones. So I was trying to embed them in the modules as well, and I don't think I did that with week 4 at all. So that's my bad.
Okay.
Yeah, these modules are getting a little bit too packed with material in some cases, and so that's why I was trying to divide them into units, like week 4 part 1 and part 2. But then we have to look between two modules. I don't know. I should cut this extra stuff out for simplicity.
Okay.
So I'm sort of open to either. Honestly, the quiz at the end. So I didn't want to have that be multiple attempts because I didn't want people to sort of go and take a stab at it without watching the video. I wanted people to be rewarded for watching the video carefully and then just working through the quiz one time. Yeah. But my goal is not to be like, what's Tim thinking, frustrated about this. My goal is to have you be able to select the answer fairly easily, just reflecting your knowledge from the video. That's my goal.
Okay.
Yeah. So I don't know if we came up with a solution, except for try not to be confusing on the questions.
All right.
Is that did I read you right on that?
Yeah.
Yeah. Okay, cool. Any other comments or? All right. I'll stop recording now.
Cool.
And